Hi, everyone. Thanks for being here. I'm excited to share with you some of the latest trends in AI and robotics. So, some headlines you might have seen. Stephen Hawking warning AI could end mankind. Elon Musk saying something very similar. Then Elon Musk also investing $1 billion in what became OpenAI, which you might have heard of. And then people saying the exact opposite. Even if it's Elon Musk and Stephen Hawking saying it, it's still not true. And a lot of money going into it. For example, DeepMind, startup out of London, was acquired by Google 5 years ago for just essentially having an amazing AI demo. They had no customers, no revenue, but amazing AI expertise, and were acquired for $500 million. Two of my former postdocs co-founded a startup called Auto for self-driving trucks. Within 6 months, it was also acquired for about $600 million by Uber. And then China has many of the most valuable AI startups these days. Most notable one may be SenseTime, which 4 years into existence was already valued at $3 billion, and by now is, I believe, at $6 or $7 billion. So, life as a professor in AI has changed a lot in this time. Before 2015, I could just quietly sit behind my computer, read some books, write some emails. Since then, everybody got interested in AI. So for example, this is a dinner a year and a half ago with Jeff Bezos at Mars, where he invites about 100 scientists who are experts in AI, machine learning, robotics, and space to learn more. This is the main AI conference, NeurIPS, which has 8,000 attendees now, up from 1,000 just several years ago. In fact, this conference sold out in less than 12 minutes, much like pop concerts. And then there's this thing. This is a painting made by an AI system. In fact, the equation behind the AI is the signature on the painting. That equation is an equation that has a random number in it, random vector in it, z. If you change that random vector, you get a new painting. And so you can now automatically generate a range of paintings, sold at Christie's for $500,000. All you have to do is run a piece of code, put in some random seeds, and hopefully a painting comes out that somebody buys. So is there some hype? For sure. No denying that. But actually, a lot of progress is also being made. And so what I want to do here is give you a little more understanding of the fundamental progress that is being made. So the first thing I want to do is look at what is driving these recent quick progression of breakthroughs. Then what are the new frontiers coming after that? And is AI here to stay, or is it just something you're excited about today, but next year you've forgotten about it? So let's think about what an AI should be able to do. Should be able to recognize that's a coffee mug. For us, it's very easy. Nobody's going to get that wrong. But what if you need to write a computer program to recognize this? Well, it's a bunch of numbers. So how do you write a piece of code that says, if this number, then that, if this number, then that? It's very hard to do. In fact, people were not succeeding at writing code directly to process these numbers. People tried many things, and the most popular thing leading up to 2012 was kind of very engineered pipelines where you extract edges and images, histograms of edges, feed that into a very basic machine learning system, and hopefully it works, but it didn't really work. Then in 2012, everything changed. Out of Jeff Hinton's lab at the University of Toronto, together with his students, he showed it's possible to train a very large neural network to recognize what's in an image. Well, what does it look like? A neural network consists of a lot of neurons, and each neuron is very simple. So a neuron just has some inputs and then generates an output. And very simple calculation happening inside the neuron. Just take a weighted sum of the inputs and feed it out. But if you make the network large enough, all of a sudden it becomes very capable if you wire it up correctly. And that's the real question here. What decision is this network going to make when you feed in this dog image? It might say cat. It doesn't know about dogs until you've actually wired it up correctly to recognize those things. The network they had in 2012 has 60 million parameters you have to set. So you can't go in by hand and set those 60 million parameters. It doesn't work. Secret is to have a lot of data. If you have a lot of data, you can feed in one example at a time. For example, feed in this dog, let it process. And initially, you don't know how to set up your network, so it probably makes a mistake. It might say cat. But then you do a backpropagation in the network, which changes the wiring, and now it knows this is a dog. You do this example after example after example, millions of examples, and at some point something magical happens. It didn't just memorize the examples you gave it, it also starts recognizing things you've never given it before. Give it a new image of a dog, and it just knows. Now I wonder, how big of a breakthrough was this? This is competition, ImageNet, organized by Stanford professor Fei-Fei Li. And in this competition, the organizers have a secret stash of images, and to participate, you send your code to the organizers. They run it on their secret stash of images and report out the error rate of your code on recognizing what's in those images. In 2010, the error rate was 30%, very similar in 2011, and traditional computer vision was not really rapidly improving on that. Jeff Hinton's group with deep learning landed right there at half the error rate. Of course, people realized this is the new approach to follow. People switched over, and it was a very fast acceleration here, where actually by now this competition has been retired because human-level error rates have been achieved. Just to be clear, human-level error rates have not been achieved in general computer vision, but for this benchmark, neural nets achieve human-level vision. Same happened in speech recognition. In fact, out of the same lab, Jeff Hinton's lab, University of Toronto, showed that you can actually do better with deep learning than traditional approaches. And the same thing happened in machine translation. Same process. You have a bunch of inputs. In this case, input would be sentence in one language, output sentence in another language. If you give it enough examples, it starts recognizing the pattern and can translate new sentences. Some things that are very advanced for humans to do, like dermatologists trying to recognize whether a mole might be precancerous or not, can be done by neural nets if you give it enough examples. Same for X-rays, recognizing whether it might be a sign of pneumonia or not. If you give it enough examples, the neural net can recognize the signs. So really what's happened is a change in programming paradigm. People used to program by writing lines of code, and that's still relevant for some applications, but doesn't work well for AI-style problems. What works well there is you lay out a large neural network, and there's a theorem that says if you make it big enough, it can represent any mapping. Of course, you don't want to make it too big, it's hard to put in a computer and so forth. But you make it big enough to represent any mapping, it's now a matter of feeding in the right data. And so programming becomes, to a great extent, finding the right data, input corresponding output, that then the neural net can be trained on. And then analyzing when it fails, what kind of new data you should go collect to continue to train it to become better, 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 better. Okay, so that's supervised learning. Supervised learning is about learning a mapping from input to output. And you give it examples very explicitly. That now works really well, and if you have such problems, you can actually hire AI experts that will make it work for you. What are the new frontiers? First big one is deep reinforcement learning. And reinforcement learning is about closing the loop in decision making. Supervised learning is in-out. But in practice, you want your systems to achieve goals, to understand what they're trying to do, not just do a reactive mapping. So a robot would need to look at the world, act based on what it sees, but it's not over. Then it looks at the result, goes again, 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 till it achieves its goal. Maybe a good meal for you to eat. One great example, not yet with a robot, was AlphaGo. In AlphaGo, you have to make many decisions to finally win the game. For the longest time, people thought this was a very hard problem to solve, would take another 100 years. Because if you think about all the possible consequences of your actions, it's going to take forever. But if you realize that this is also an image recognition problem, white pixels, black pixels, empty pixels, and you can recognize whether a situation is good for you or bad for you, you only need to think one step ahead. And that allows you then to play with today's computers instead of needing computers that can think very far ahead that we'll only have in the future. While DeepMind was working on AlphaGo, at Berkeley we were working on having robots learn from their own trial and error. So we're going to watch here, for the first time in this session, is learning in action. So what do you think is going to happen? This robot has a neural net to control it, but it's randomly initialized. Random control is not going to succeed. It's going to fall over. But then it's going to try many times. And sometimes be a little more lucky. And when it's lucky, it's going to backpropagate from that to change the wiring of the network to make it more likely to happen again. That will have been one iteration. So at iteration 0, it falls over. At iteration 10, it falls over quite a bit later. At 40, even later. At 160, even later. And at 2000, it's learned to run. The beauty here is that nothing is specific about the two-legged robot. You can run the same code to train a neural network to control a four-legged robot, or to train a two-legged robot to get up, or to train a neural network to play Atari games. Then we put this on a real robot. So what you see here is Brett, the Berkeley robot for the elimination of tedious tasks. Brett lives in the AI lab at Berkeley and is learning to put the block in the matching opening. You might say, oh, I can do this in first attempt, and I really hope you can. But keep in mind, you've done many other things in your life before. This robot is starting from scratch. Imagine a baby just born, and within the first hour of being born is putting blocks into matching openings. That's kind of what's happening here. Then from this result, we started a collaboration with NASA. NASA Ames just next door here, next exit on the highway. And what you see here is the Super Bowl robot. And through reinforcement learning, this very non-intuitive robot, very hard to design a controller for, but through reinforcement learning, it was possible to learn a neural net that can control it, make it move. This robot's supposed to do exploration of new planets. And then at OpenAI, very similar ideas were developed even further to then showcase it's possible to do in-hand manipulation. Now, the one thing I want you to take away from all this is that actually, the things that might seem easy to us as humans are actually really hard to get computers, robots to do. Often the things a 3-year-old can do are actually the hardest to get a robot or a computer to do. And so this is a good example of something all of us could do easily, but was a long-standing problem to get to more advanced in-hand manipulation, and now with reinforcement learning, it's possible. Well, think about robotic automation. Happens a lot in car manufacturing, electronics manufacturing, clothing manufacturing, but it's all repeated motion. And with these new capabilities, this is going to change, because all these problems are very important problems that we need solved. We need automation. There's so much demand for faster deliveries, better turnaround, everything, but all these problems cannot be done with a blind robot like we use in car manufacturing. You need a robot that can see, adapt, and so forth. But what I just showed you, this is starting to become possible. And so we'll see a new wave of automation coming. What will it enable? Robots with eyes. Robots that can handle new objects they've never seen before, including the long tail of the real world. And robots that can adapt on the job. If something doesn't go exactly right, they'll reinforcement learn and be better the next time, rather than going to a deadlock where they keep doing the same thing over and over and over and fail over and over and over. With that in mind, 2 years ago, actually, myself, together with 3 Berkeley PhD students, OpenAI research scientists, Chen Shi, Duan Yan, and Jiang Tianhao, we started Covariant. And that's exactly what we're doing there. We're building the next generation of AI to enable robotic automation that can see, adapt, and handle the wide range of things you see in the real world. Now, what else is new on the frontier? Unsupervised learning. Unsupervised learning, because this is somewhat the opposite problem that we've looked at so far. So far, we looked at neural nets taking in some complex sensory information and outputting something small, a conclusion. Now we're going to flip the script around. We'll go from something small, a random code, and try to generate something like a painting. Well, can we do this? Well, you can easily set up a neural network in PyTorch, TensorFlow. It'll generate images, but they're not really that good-looking images. This is a 10 by 10 grid of images. But if you train the network the right way, through something called generative adversarial networks, here's what happens. Now, for each new random seed, we get a different image, and they're getting better and better and better, more and more realistic. When you look at this, you might say, well, that's not that realistic. I'm not that impressed. But actually, the whole AI community was super impressed when this came out in 2016 and realized this was a sign of much bigger things to come. And indeed, it didn't take long. Just a couple years later, this is what we get, all automatically generated. And if you go to this website, thispersondoesnotexist.com, you refresh, you get a new person. That's exactly what I did last night. I kept refreshing, get new people, put them on the slide. You can do not just from random code to new image, but also image to image. So here you have a horse turned into a zebra. Now, let's see. Let's do a quick raise of hands. Who here is a really good dancer? Raise your hands. Wow, nobody raising their hands. One person raising their hands. Okay, we got one really good dancer here. Okay, now, the student who made this is not a good dancer, but he thinks it's a good idea to have cool dance videos of himself. And so he figured, if I can turn a horse into a zebra, I can turn a professional dance video into a dance video of myself dancing. And that's exactly what he did. So Tinghui Zhao and Caroline Chen, here, this is a calibration motion. This everybody can do, and now it's fake. The top left is the source video, is the professional dancer. The other two are fake. But it looks real. And so all of you, except for that one person who do not have good dance videos of yourself yet, now is your chance. Tinghui actually started a company doing exactly that based in San Francisco, helping people with their online presence to look much cooler than they could be in the real world. Now, different people, different definitions of cool. Maybe you think ballet dancing is the thing you want. No problem either. This was image generation. You can do something very similar with text generation. If you train a neural net on enough text to generate the next character, then you can give it a new prompt and ask it to generate next character, next character, next character. Here's a prompt, and here's what it generates. And if you read this, you look at this carefully, it's actually looking like a real news article. It starts with a little more detail about the prompt, then it has a quote from a high-ranking official saying something about it that is really important, need to fix it, and then some more detail. Honestly, it's hard to know whether this is real or not. The only way you're going to know whether it's real or not is by actually looking at what happened in the real world. From just the text, you can't say, well, this is clearly a fake story. In fact, so realistic, OpenAI, who built the system, decided not to release this system when they came out with the result because there was a fear that people would generate a lot of fake stories that people cannot distinguish from real stories. So, we've seen a lot of breakthroughs, and I would say what's most interesting about what we've seen in the last 5 years in AI is not just that we've seen breakthroughs that were pretty much every time unexpected. Something happened people thought was impossible to do anytime soon, and then it already happened very quickly. And so the question we can ask, is that going to continue to happen? Or have we seen the breakthroughs, and now we just commercialize what we have, but there will be no new research breakthroughs? Well, let's think about that. So, what's driving it? I think because of what's driving it is here to stay. Because what's driving it is data. We only get more data. Compute. Well, that's a bit of a question. And innovation. People will keep innovating. So the real question mark here is, are we going to get new compute? More compute than we have today. Why? Because research breakthroughs happen essentially when scientists get to run experiments overnight, look at them the next morning, see what happened, change their setup, run a new experiment. AI is a very experimental science. For none of these breakthroughs I showed you, somebody proved, oh, this is guaranteed to work, and now ran it. No, they had to iterate over and over and over till it worked. And so fast iteration is key to making these breakthroughs. So if we have more compute, we'll be able to do new experiments nobody can run today, new experiments next year that are going to be the next breakthrough. Moore's law is supposed to give us more compute, but some people say it might start tapping out. Not clear. Moore's law is by making transistors smaller. So the question is, can we keep making them smaller or not? Not clear. But you can do other things. You can use the existing fabrication technology and realize that CPUs, GPUs don't use the transistors all that effectively for neural net compute. They can do dedicated designs for neural net chips. Many companies doing this, including in China actually, and they believe they can get to 1,000 times the compute in the same chip, same fabrication technology we have today. That would be 30 years of Moore's law if that succeeds, just in one redesign. And then you can network compute, which will allow you to run bigger and bigger experiments. The big breakthrough in image recognition in 2012 used a large amount of compute, but actually AlphaGo 0 used 300,000 times more compute. And a lot of money is made with AI these days, so there will be a forcing function for companies to try to design those chips and the networked compute. So we covered all these topics. Now, the conclusion, I think, is we will see at least another 5 to 10 years of AI breakthroughs because we'll have drastically more compute in the next 5 to 10 years than before. If this is all interesting to you, I have a recommendation. If you want to keep learning more, I highly recommend you subscribe to this newsletter. It's written by Jack Clark. Jack Clark used to work the AI beat at Bloomberg, then became communications director at OpenAI. Every Monday morning, a newsletter comes out with the latest economical, political, technical happenings in AI. I read it every week. It's always a really good read. It takes you a couple minutes to just skim and know what the latest is that's been happening. If you want to dive under the hood and you want to learn the technical things, here's a list of materials. All of these are freely available or at very low cost available online. Lecture videos, projects you can work through, homework you can work through. You can actually learn this all on your own if you want to. Requires a lot of motivation, but the material is all available for anybody to study. And if you'd like to reach out to me, that's my email. We're always looking for more partnerships at Covariant and always looking for more collaborations at Berkeley. Thank you.